Good morning children. Welcome to Greater Chennai Corporation online class. இன்னைக்கு வந்து 12th standard physicsல electric flux and Gauss Law நம்ம பார்க்க போறோம். Electric flux னா என்னன்னு first define பண்ணிடுவோம். It is the number of electric lines of force crossing a given area kept normal to the direction of electric field lines. Again, let me read it out again. It is electric flux is defined as the number of electric lines of force crossing a given area kept normal to the direction of electric lines of force. And it is denoted by the Greek letter phi e. Phi e ன்னு இதை pronounce பண்ணணும் நம்ம. அப்புறம் இதனுடைய SI யூனிட் வந்து Newton meter square coulomb per -1. இது நம்ம derive கூட பண்ணலாம் பின்னாடி. It's a scalar quantity and it can be both positive and negative. Okay, just based on the definition, நம்ம first outline ஒரு electric flux னா என்னன்னு quantitative-ஆ நம்ம வந்து புரிஞ்சுப்போம். So, let us assume a source charge plus Q. You all know, இந்த source charge plus Q ல இருந்து electric lines of force வந்து it will emanate outside. So, electric lines of force வந்து I have to draw in all directions. Let me draw the electric lines of force. So, from a point charge, positive charge plus Q, the electric lines of force emanate outside equally in all directions. Now, we are going to define electric flux. Electric flux define பண்ணனும்னா you have to imagine an area, a given area, and it should be kept normal to the direction of electric lines. So, let me draw an area. Say, name this area as A. Let me draw another one area. Say this as B. Let me protrude this. So, I have considered two different areas, area A and area B. Area A and B both are of equal area. The area of A and B are equal. Let's just assume like that. But this area A is placed very near to the source charge and area B is little far away from the source charge. Now, as per the definition, number of electric lines of force crossing a given area kept normal to the direction of electric field. I have kept these two areas normal to the direction of electric field, and let me count the number of electric lines of force crossing these two areas normal to the direction of the electric field. So, if you just count, say 1, 2, 3, 4, 5, 6, the number of electric lines of force crossing this area A is say 6. But if you take this area B, the number of electric lines of force crossing this area B is only 3. Now, I told you we have to represent the number of electric lines of force, that is electric flux is represented by the letter phi E. So, say the electric flux through A is phi A and electric flux through B is phi B. So, now I have counted and shown you the number of electric lines of force crossing A is, we counted it to be 6 and crossing B is only 3. So, naturally, electric flux phi A is greater than phi B. So, what do we interpret from this? When the area is nearer to the source charge, the electric flux is also more. That's why electric flux of area A is more than the electric flux of area B. This we have even studied previously. Electric field E is more at any point which is nearer to the source charge than for points which are far away from the source charge. So, wherever the electric field is more, the electric flux will also be more. So, this is only a quantitative definition for electric flux. So, if we want to have the precise definition for electric flux, we have to consider, we all know that the point charge will only produce non-uniform electric field. Just for understanding we have taken this example. Now let us give the precise definition for electric flux. For this we will take uniform electric field. Say this is a uniform electric field. Uniform electric field, as you all know, have to be drawn as parallel lines, and the direction I have specified using the arrow mark. Now let me give an area. In order to define electric flux, I have to draw a area. So electric flux phi E is given as EA. E is the electric field and A is the area vector. Why do we call? Normally we know area is generally a scalar because area is generally length into breadth. But in this case, by definition you can see the given area must be kept normal to the direction of electric field. So it is more important, we are more concerned about the orientation of the area with the electric field. So area is not only just a scalar, it is a vector. That is why we call this as an area vector. And area vector, it is nothing but the magnitude of A with the direction, that is denoted by n cap. So let me draw the direction of the area. This area, this is the plane which is kept, see, it is kept normal to the direction of the electric field, and the direction of the area vector is denoted by the normal unit vector n cap. The direction must be drawn normal to the plane of the area. So now from the diagram itself it is very clear. Apply the definition. The number of electric lines of force crossing normal to the area plane of the area is kept normal to the direction of the electric field. So here we have phi E is equal to EA. Now let us take, let us take this example. This is the electric field. Now I am taking this area, this is the area A, this area, here I have kept it normal. So you have got the formula phi E is equal to EA. Let us assume this area is kept parallel to the direction of the electric field. Say the electric field is acting in this direction and the area is also placed parallel to the direction of the electric field. This is the area. Now how will you draw the direction of the area vector? Perpendicular to the plane of the area, like this. So by definition electric flux is nothing but the number of lines of force crossing normal. But can you see any lines crossing normal? No, there are no electric field lines normal to the area. So here phi E is 0. So now let us consider another one example. At all times the plane of the area may not be either perpendicular or parallel. It may be inclined to the direction of, inclined with the electric field in most of the cases. So let us take this case. This case in which the area A is inclined at some angle theta with the direction of the electric field. Now how will you draw the angle theta? Angle theta is the angle between the direction of the electric field and the direction of the area vector. So let me draw direction of electric field, already we have specified here. Direction of the area vector, you have to draw the normal like this. So the angle theta between the electric field E and the normal to the area vector is theta. So here, as per the definition, electric flux is nothing but the number of lines crossing normal. So here the electric field should be resolved into the electric field vector must be resolved into two components. One along E cos theta, along the direction of the area vector, another E sin theta parallel to the area vector. So out of these two components, just you see which is normal. Only E cos theta is normal to the area, E sin theta is parallel. So this E sin theta component will not contribute for the electric flux, only the E cos theta component, which is normal as per the definition, normal, only the normal component will contribute for the electric flux. So electric flux E is equal to, instead of here we wrote EA, here there are no flux lines normal, so we wrote 0. Here normal flux lines is only E cos theta into A. So this I can write as EA cos theta. Here E is the electric field and A is the area, and theta is the angle between E and A, angle between the electric field E and the area vector. So phi E is equal to EA cos theta. Now we all know A vector dot B vector is equal to AB cos theta. So apply this formula here. For this we can write phi E as E vector EA cos theta, which we can write it as E vector dot A vector. So there are two vectors. The product of two vectors leads to a scalar. So we told initially, in the beginning we told scalar quantity. Electric flux is a scalar quantity. It is just a mere number. It only gives us the number of electric lines of force crossing normal to the direction of the electric given area, through a given area, which is kept normal to the direction of electric field lines. So this is the general formula. This is the precise definition for electric flux. Electric flux phi E is nothing but E vector dot A vector, which is EA cos theta. So we will go to the next topic. Now we have derived the correct expression for the electric flux phi E is equal to EA cos theta, which is nothing but E vector dot A vector. Now using this general expression for the electric flux, we can arrive at these two relations based on the angle theta. Now let us find the angle theta for the first case. For the first case, what is this theta? Theta is the angle between the area vector and the electric field. Area vector is in this direction. Electric field is also in this direction. So both E and area, direction of area vector are parallel. Therefore in this case theta is 0. So you just apply this theta here. We will get phi V is equal to EA cos 0. So cos 0 is 1. So we have EA. So phi E is equal to EA, which we already wrote for the first case. Now take the second case. Second case, what is the angle between n vector, the unit n cap, the area direction of area vector, and E? It is 90 degree. Theta is equal to 90 degree. So substitute in this, phi E is equal to EA cos 90. Cos 90 is 0. So the electric flux is 0, which we arrived previously. So using hereafter, wherever we want to find the electric flux, we can use this general expression for electric flux phi E is equal to E vector dot A vector, which is EA cos theta. So using this formula, we will try to solve this problem. Calculate the electric flux through the rectangle of sides 5 cm and 10 cm kept in the region of a uniform electric field 100 Newton Coulomb power minus 1. The angle theta is 60 degree. If theta becomes 0, what is the electric flux? So here it is a uniform electric field. So let me draw the uniform electric field. Here the electric flux we want to calculate through an area. Area is a rectangle of sides 5 cm and 10 cm, and it is kept at an angle of 60 degree. It is inclined. So I have to draw the diagram as a third case which I showed you previously. So this angle, this angle theta is 60 degree. Angle theta, which is the angle between the electric field vector and the area vector, direction of area vector, is 60 degree, and the breadth and length they have given us 5 cm and 10 cm. So 5 cm and 10 cm. So area A will be 5 into 10, which is 50 centimeter square, you can convert this into meter square. 50 into 10 power minus 4 meter square. This is the area. Okay. Now we have got the area and it is kept in a electric field, uniform electric field whose value E vector is 100 NC power minus 1. And the angle theta they have given as 60 degree. Area A is 50 into 10 power minus 4 meter square. So using these we can use the formula. What is the formula we saw? Phi E is equal to, the formula is phi E is equal to E vector dot A vector, that is phi E is equal to EA cos theta. Now substitute for E as 100 into area is 50 into 10 power minus 4 into the angle is 60 degree, that is cos 60 degree. So cos 60 is half. So 100 into 50 into 10 power minus 4 into half. So we have 2500 into 10 power minus 4. That is phi E is equal to 0.25 Newton meter square coulomb power minus 1. So how you got this unit also? You can just substitute phi is equal to EA, no. So E is unit of E is Newton coulomb power minus 1. Area is meter square. So unit of phi E is Newton meter square coulomb power minus 1. So the value phi E we got as 0.25 Newton meter square coulomb power minus 1 when this area is inclined at an angle theta 60 degree. Now they have asked again, if theta becomes 0, what is the electric flux? Becomes 0 means how we have to place the area? Normal. So it should be placed like this. Normal. That is both n vector and E vector will be acting in the same direction. So in that case 2, if theta becomes 0, both E vector and A vector are parallel. In that case theta is equal to 0. So phi E will be E, you substitute for E as 100 into A is 50 into 10 power minus 4 into cos 0. So what will you have? Phi E is equal to 100 into 50 into 10 power minus 4 into cos 0 is 1. So you will have 5000 into 10 power minus 4, which is 0.5 Newton meter square coulomb power minus 1. So in this problem we have used the formula phi E is equal to EA cos theta. So this is regarding electric flux. Electric flux, how will you define? It is the number of electric lines of force crossing normal to a given area, which is kept through a given area which is kept normal to the direction of electric field lines. So this formula you have to remember, and using this formula you can solve the problems. Okay children, now we will see, till now we discussed only with a uniform electric field, but at all times we won't have uniform electric field. Now we will see the electric flux through an arbitrary area which is kept normal to the non-uniform electric field. Let me say, what is this arbitrary area? Previous discussions we placed a rectangular area, a uniform rectangle or a square, any shaped area we can take. So in that we took a rectangularly shaped area, but every time the area may not have a regular shape. It may be arbitrary, like you may have the area like this. It may not be flat also, it may be curved, and It may not have a regular shape also. Like this, it may have an irregular shape. Such an area is called as an arbitrary area. And the electric field which is crossing this area is also not uniform. It is a non-uniform electric field. In such case, how will you find the electric flux? So, the treatment is very simple. Like we have to divide this area into very, very small area elements. So, I have just denoted few area elements here. Del A1. Del A2, del A3, del A4, etc. up to del AN. The whole given arbitrary area is divided into smaller area elements, and the electric field also, it is not same at all points. Say in this very small area element del A1, the electric field is E1, and for this smaller area element del A2, electric field is E2. Del A3 it is E3. Similarly for del AN it is EN. You have to find the electric flux for each smaller area elements, and the total electric field is got by the summation of all these electric flux due to these smaller area elements. So the equation must be written as E1 vector dot del A1 vector plus E2 vector dot del A2 vector plus etc. up to En vector dot An vector. So we can write this as a summation I is equal to 1 to n in the similar way how we wrote for electric field. The same way this equation can be written as a summation I is equal to 1 to n Ei vector dot del Ai vector. Here again in this arbitrary area there are n number of area elements. So we have this expression, and these area elements, if we consider it, is very, very small. The area element del A is very small in the sense it tends to 0. So this, in such case, this del A we can write it as dA, and the summation will become into an integration. So we have the expression for electric flux as integral E vector dot dA vector. This is the simple expression for the electric flux phi E through an arbitrary area which is kept in a non-uniform electric field. Now, initially we saw for a regular shaped area, then we saw for the that is non-uniform electric field for any arbitrary area. Now the next case we are going to discuss is, every time it may not have a flat area, it may be a closed surface, the area may be a closed surface. So in such a closed surface, supposing we want to find the electric field through a closed surface which is kept in a non-uniform electric field. In such case, how will you find the net electric field? See, this is the diagram which shows the closed surface which is kept in a non-uniform electric field. Just for simplicity, we are going to discuss about this. Just for understanding, I have drawn only one single electric field and I have drawn a closed surface. Here, the difference between these two is here there is only a one surface. The electric field just goes through the arbitrary surface. But since this is a closed surface, we have to argue in two ways. One, the electric field entering the closed surface and the electric field leaving the closed surface. So initially, while in the beginning I told you electric flux can be both positive and negative. Here we are going to arrive at such a case where the electric field is both positive and negative. So let us say at the point A, the electric field enters the closed, this electric field enters the closed surface A, and at the point B it leaves the closed surface. So here we want to discuss, we have to take two different area elements, one area element at the point where the electric field enters and the other area element where the electric field leaves the closed surface. Here I have drawn the area element and we have to draw the normal to the area n, and electric field is in this direction and the angle between E and n is theta, which is greater than 90 degree. at the place where the electric field enters the closed surface. Now see this point where the electric field leaves the closed surface. I have drawn the small area element. I have drawn the the direction of area vector and the electric field. Now see here the angle between E and N, it is theta, which is less than 90 degree. So at all points where the electric field enters the closed surface, so at A and at B, electric line enters the closed surface. Here electric line leaves the closed surface. Here theta is greater than 90 degree. Here theta is less than 90 degree. You all know cos 0 is 1, cos 90 is 0, cos 180 is minus 1. So you can very well understand that less than 90, for all angles less than 90, the value is cos of that angle is positive. Here it is positive. And for all angles greater than 90, it is negative. So if theta is greater than 90, then cos theta is negative. If cos theta is negative, what is phi e? Phi e is nothing but Ea cos theta. So if cos theta is negative, phi e is also negative. Phi e will also be negative. In this case, at the point P where the electric line leaves the closed surface, theta is less than 90 degree. So for all theta less than 90 degree, phi e is cos of that angle is positive. So if cos of that angle is positive, phi e will also be positive. Phi e will also be positive. So theta is greater than 90, cos theta is negative. Cos theta is negative, now phi e will also be negative. If theta is less than 90, cos theta is positive, that is phi e will also be positive. So we can very well understand, what do we understand from this? Electric flux is negative at all points where the electric lines enter the closed surface, and it is positive at all points where the electric lines leaves the closed surface. We have got the expression for closed surface, the electric flux through a closed surface, phi e is equal to, for an arbitrary surface it is integral E vector dot dA vector. The same expression we can write for closed surface, just if we indicate the closed surface by drawing a circle over the integral symbol. Phi e is equal to closed integral E vector dot dA vector. Phi e is equal to closed integral E vector dot dA vector. Now let us just apply this for a point charge, and we are going to arrive at the Gauss law. So Q is a point charge, and we are going to imagine a closed surface, a closed sphere around this point charge. This imaginary closed surface is called as the Gaussian surface, and it is spherical in shape. So according to the formula, phi e is equal to closed integral E vector dot dA vector. Now this E vector dot dA vector is nothing but EdA cos theta. Now since it is a point charge, the point charge will have electric field emanating, this is plus also, it has electric field emanating in all directions over the whole sphere. So we can take the electric field at all points which are at equal distance from the point charge as uniform. The electric field at all points on the sphere is E, which is uniform, and the direction of electric field is directed radially outward. So if I want to find the electric field, I have to first divide this sphere, the Gaussian sphere, into very small area elements. Just for example, I have drawn 3 different area elements. This one small area element here, all these area elements are at equal distance, and the electric field is normal to the, at this point the electric field is normal to the sphere, the surface of the sphere, and the area vector will also be normal to the surface of the sphere. So both the direction of area vector n cap and the direction of the electric field will act in the same direction. This is the case at all points on the sphere. If you take the area element at this point also, direction of E vector and n cap will be in the same direction. So, the angle between E vector and n cap, that is the angle between the electric field and the direction of area vector is 0, that is theta is 0. So, substitute here 0, we will have phi E is equal to closed integral E dA. I have already told you E is same at all points on this imaginary Gaussian sphere. So, you can take this E outside the integral symbol, you have closed integral dA. What do this closed integral dA represents? It represents the whole area. The dA, if you integrate dA, you will have A. A is nothing but the whole surface area of the imaginary Gaussian sphere. The surface area of the Gaussian sphere integral dA is 4 pi r square, and at any point the electric field is given by the formula which we have already derived. Electric field at any point at a distance r from the point charge E is equal to 1 by 4 pi epsilon naught q by r square. So, substituting these two in this expression, you will have phi E is equal to, for E I have substituted 1 by 4 pi epsilon naught q by r square into integral dA, closed integral dA is 4 pi r square. 4 pi will get cancelled, r square will also get cancelled. So, phi is equal to q by r square. Here from this expression we see this q is nothing but, so we will get the final expression as phi E is equal to q by epsilon naught. So, this is the final expression for the electric flux through any, this is the Gauss law. Actually here this charge q is nothing but the charge q which is enclosed by the Gaussian surface. So, we can write this expression as phi E is equal to q enclosed by epsilon naught. So, this is the Gauss law, and the Gauss law can be applied for any arbitrary closed surface. Like here in the, for derivation purpose I have taken this point charge q which is enclosed by a imaginary Gaussian sphere which is spherical in shape. At all times it may not have a regular shape. It may be, the closed surface may be of any arbitrary shape like this A1, A2, A3, like this. It can be of any shape, and this equation applies as well for any arbitrary surface. So, the Gauss law is stated like this: if a charge q is enclosed by any arbitrary closed surface, the total electric flux is 1 by epsilon naught times the charge enclosed. So, if a charge q is enclosed by an arbitrary closed surface, the total electric flux is 1 by epsilon naught times the charge enclosed. So, this is Gauss law. Okay children, now we have arrived at the Gauss law. Phi E is equal to q enclosed by epsilon naught. What are all the important discussions we need to see before concluding? This phi V, just by seeing the formula you can understand this phi E, which is the electric flux, depends only on the charge which is enclosed by the closed surface, that is the Gaussian surface. It depends only on the charge which is present inside the Gaussian surface, and it does not depend on the charge which is present outside the Gaussian surface. So, supposing this is the charge enclosed, this electric flux depends only on q. Supposing if you have any other charge q1 outside the Gaussian surface, it will not contribute for the electric flux. That is, it is independent of the charge present outside the Gaussian surface. And also the location, the charge which is present inside the Gaussian surface, it may be located anywhere inside the Gaussian closed surface. The location, it is independent of the location of the, it is independent of the location, it is independent of the location of the charge which is present inside the closed surface, and also it is independent of the shape of the closed surface that we have discussed already. The closed surface may be of any arbitrary shape. And also the second point, that this is what I wanted to tell you, it is independent of the location of the charge which is present inside the closed surface. Inside the closed surface, the charge which is contributing for the electric field can be present anywhere. So, the first point is flux depends only on the charge which is, it depends only on the charge which is present inside the closed surface. If we have any charge which is present outside the closed surface, it will not contribute for the electric flux. And also it is independent of the shape of the Gaussian surface. It may be of any arbitrary shape, and also the second point is it is independent of the location of the charge inside the closed surface. This Q can be present anywhere inside the closed surface. Now the last one is the shape of the Gaussian surface depends on the configuration of the charge. Like here I have drawn two examples. For point charges, normally we will take the Gaussian surface as a sphere. Supposing if we have the charge which is stored in a wire, like this, in this kind of configuration of the charges, surrounding this charge, we will take the Gaussian surface in a cylindrical shape. So depending upon the shape of the enclosed charge, we will take the shape of the Gaussian surface. Now finally, from this expression, we have to clearly understand one thing. Phi E, which is nothing but the electric flux, is nothing but the closed integral E vector dot dA vector, which is equal to Q enclosed by epsilon naught. This is Gauss law. And here this E, which is the electric field, it is due to charge present both inside and outside the Gaussian surface. So this electric field, it may be due to all the charges. It is due to all the charges which is present both inside and outside the Gaussian surface. But this Q enclosed, it only represents the charge which is enclosed by the Gaussian surface. Enclosed by the Gaussian surface. So with this, we come to the conclusion of this Gauss law and electric flux and Gauss law. You have to remember this formula clearly, children. The whole class we have dealt only with the formula phi E is equal to closed integral E vector dot dA vector, and in Gauss law it is Q enclosed by epsilon naught. And using this expression, we are going to see 4 applications of Gauss law, which we will see in the next class. Thank you, children.